You walk into a sweltering room, grab the AC remote, and immediately crank it down to the absolute lowest setting. Most of us do this because of a deeply ingrained assumption. We think a lower temperature setting forces the machine to cool the room faster. Unlike a car that accelerates smoothly, your AC has two settings: off or 100% capacity. The remote sets a target, not intensity. Air constantly blows out at 10 to 14 degrees. Setting it to 16 just commands the machine to never stop running, which brings up a strange contradiction. If human nature constantly pushes us to demand faster, colder cooling, why did engineers hardwire almost every AC unit in the world to stop exactly at 16 degrees? Why not 10 or even 0? The modern air conditioner is a machine bound strictly by physical limits, designed explicitly to protect itself from the misunderstandings of the people using it. To understand those limits, we have to look at what an AC actually does. It doesn't create cold air. It acts like a heat vacuum, extracting thermal energy from your room and dumping it outside. The component doing the heavy lifting is the evaporator coil, a network of super-cooled pipes that absorbs ambient heat. But there is a crucial side effect. As warm air hits the freezing coil, it loses its capacity to hold moisture. It's the exact same process that causes water beads to form on the outside of a cold glass of water on a hot summer day. Effective air conditioning relies entirely on this physical reaction. It is pulling heat, but it is also actively wringing water out of the air. This chart shows the dangerous thermodynamic relationship between the room's target temperature and the machine's internal mechanics. To force a room below 16 degrees, the AC must drop the internal coils past the freezing point. When this happens, all that condensed moisture instantly solidifies into a thick layer of ice. This ice layer acts like a thick, insulating blanket. It completely blocks the coils from absorbing any more heat from the room, choking off the system's airflow until the internal mechanics simply fail. If an air conditioner actually obeyed your demand for a 10-degree room, the machine would literally suffocate itself in its own ice. That 16-degree limit is a deliberate engineering failsafe. It is the lowest possible setting that prevents the coils from freezing, while still delivering the maximum amount of cold air humans demand. Historically, air conditioning wasn't even designed to optimize human comfort. It was invented strictly to control moisture and protect sensitive materials. In 1902, Willis Carrier built the first modern AC to stop high humidity from warping paper and ruining ink in a New York publishing house. Even if you could bypass the mechanics today, human biology gets in the way. Dropping a room below 16 degrees actually forces your body to work overtime to generate heat through shivering, defeating the purpose of a comfortable indoor environment. 16 degrees is a carefully calculated compromise. It honors the machine's origins, respects human biological limits, and prevents mechanical suicide. Leaving your unit set to 16 degrees on a hot day carries a heavy financial and mechanical cost. It forces the compressor to run without a break, severely shortening the lifespan of your appliance. The optimal sweet spot for both your wallet and your comfort is actually around 24 degrees. 24 degrees cools the room at the exact same speed as 16 degrees, but it actually allows the machine to safely rest once the job is done. True comfort comes down to understanding the physics of the machines we use every day and respecting the boundaries designed to protect them and us.